My name is Spiwe Sibanyoni, and I am back again to be with you for lesson number 4. And we are continuing with Newton's laws of motion. And today in particular, we will look at Newton's third law of motion. And after looking at Newton's third law of motion, we will then review what we learned from Monday, Tuesday as well as Wednesday. That is on Newton's first law as well as Newton's second law of motion. We will read to how this particular laws also relate to each other and so on. So without wasting any other time, let us proceed. Right. So here we are, and today we are doing on the third law of motion, and furthermore we will review Newton's first law of motion as well as Newton's second law of motion. Right. Now the outline for today's lesson looks like this. We'll have an overview of Newton's third law as per your examination guidelines, and then we will learn Newton's third law, and thirdly we will apply Newton's third law, and lastly I will be reminding you of how you need to write. Now in our overview, this is essentially what you need to know, and you must be able to state Newton's third law of motion. And there it is stated for you, but we will state it further as we continue with our lesson. But it tells us when object A exerts a force on object B simultaneously exerts a force on object A of equal magnitude but in the opposite direction. Right. We will explore more of this particular law to state it. 5 exercises that elaborates further on. And we must also be able to list the properties of action, reaction pair of forces. Now, let us get on with it and start to learn more about Newton's third law of motion. Now, this law states when object A exerts a force on object B, object B simultaneously exerts an oppositely directed force of equal magnitude on object A. Right, so that is how we state the law. And remember, this is how it is in the examination guidelines, and this is how you must write it, right? Don't take it from the textbook, you take it from the examination guidelines, because this is how we are going to mark you. Now, what does this mean, right? It basically tells us that when there's an object, and let's say that object, you call it A, and let us assume that object is a wall, and let's say we have object B, and that object is a car. Now, if a car crashes on the wall, what basically happens is the car is exerting a force on the wall, but at the same time, the wall is exerting a force on the car. And the force that the car exerts on the wall is exactly equal in magnitude to the force that the wall is actually exerting on the car. But the two forces, even though they are equal in magnitude, they act in opposite directions. In other words, let us say your car was moving to the left. Now, when the car crashes on the wall, basically it tells me that the force that the car pushes on the wall, exerts on the wall, is acting to the left. But the force that the wall exerts on the car, pushes the car with, it acts to the right. So the two forces are equal in magnitude, but they are definitely acting in opposite directions. Furthermore, the one force is acting on the wall, the other force is acting on the car. Even though they have equal magnitude, they do not balance each other. They don't give us a net force of 0. And why do they not give us a net force of 0? It is because these forces act on different objects. One force is acting on the car, one force is acting on the wall. And therefore, the forces, we cannot say, because the magnitudes are equal and the directions are opposite, then the forces balance each other. They can't be balancing each other because they are acting on two different objects. And because the two forces, meaning the force that the car is experiencing because of the wall, and the force that the wall is experiencing because of the car, those are two forces. So we say these forces actually come in pairs. Now, what does this mean as well? It means these forces are action, reaction pair of forces. Now, why are we calling them action, reaction pair of forces? Which one is the action force and which one is the reaction force? Now, the car is crashing into the wall. So the force that the car exerts on the wall, in other words, the force that is acting on the wall, we call it the action force. And then the force that the wall exerts on the car is what we refer to as the reaction force. In other words, one force is an action force, which is the force that the wall is experiencing, the force that is exerted by the car on the wall. And the reaction force is the force that the wall exerts on the car. Meaning, it is the force that is experienced by the car. So those are reaction, they are action-reaction pair of forces. And these here, these two, those are the properties of these action-reaction pair of forces. Because the forces in a pair are equal in magnitude and they are acting in opposite direction. In other words, excuse me about that, if the wall exerted a force of 1,000 newtons, rather if the car exerted, it means the wall also exerted a force of 1,000 newtons on the car. What else does this mean? It also tells me that if the car exerted 1,000 Newton force on the wall to the left, then the wall exerted 1,000 Newtons on the car to the right. In other words, those two forces are equal in magnitude, but they are definitely opposite. And it also tells us the forces in a pair, they act on different objects. And that is true because one force acts on the wall, the other force acts on the car, right? So they act on different objects. Now, you know, when it is simply abbreviated, when we just want you to remember it, basically we just say, for every action, there is an equal and opposite reaction. So that is basically a summary of that. Now, let us explore Newton's third law of motion further. Now here we have a number of different scenarios. Now, with this number of different scenarios, we consider the law of motion. Now, let us look at the first diagram. There, we have an interaction between a person as well as an object. Now, we can see that the man there, very strong, like Mr. Sibanyoni, is pushing on the object. And what does the object do? It also pushes the man back. Now, this object is experiencing a force, a pushing force because of the man. So the force here, this force, is that pushing force by the man. Now it is acting on this object. But what does the object do? It pushes back the man. So we can also see that then this force here is acting on the man. Now, the two forces, this force that is acting on the object and this force that is acting on the man, they are equal in magnitude. And that is why there, your arrows actually are of the same size, because the force acting on the object is actually equal to the force that is acting on the man. Now, this force that is acting on the object, we can see it is acting to the right. And this force that is acting on the man, it actually happened here. If we say this man is object A, then it means object A exerted a force on object B. Then object B simultaneously exerted a force of equal magnitude that is oppositely directed. In other words, the man's force, meaning the force that the man is exerting on this object, is our action force. And the force that the force that the object exerts on the man is our reaction force. So these are two forces, and because there are two forces, we say they are action reaction pair of forces. Now, you should be able to see that they are also acting on different objects. One force is acting on the object, and one force is acting on the person, on the man there. So you cannot say these two forces balance each other. You cannot say these forces give you a net force of 0. Why? Because they are acting on two different objects. And those are those properties of action-reaction pair of forces. Is to say, one property, they act on two different objects, and also they have equal magnitude, and they act in opposite direction. Now, what you can also see is there you've got a shuttle, right? And it is moving around, orbiting. the earth. Now, when a shuttle is moving there, the earth attracts it. Now, when the earth attracts it, we know that force, we call it the force of gravity. This shuttle will be attracted towards the center of the earth. Now, if the shuttle, rather, if the earth is pulling the shuttle downwards, right? It's exerting a downward force on the shuttle. The shuttle as well will exert an upward force on the earth. So the shuttle, rather the earth, is attracting the shuttle towards its center with the force of gravity that is acting downwards. So what will the shuttle do? It will also exert a force on the earth. And that is why this force there is called the force of the earth on the shuttle. And this force is called the force of the shuttle on the earth. So what you can see is that if the earth exerts a force on the shuttle simultaneously exerts a force on the earth. And these two forces will have an equal magnitude, but they will act in opposite directions. And we can see the force that the earth exerts on the shuttle, that downward force, that force is a downward force, and the force that the shuttle exerts on the earth, we can see that it is an upward force. Are we together? Right. So they tell us there, as a result, the two forces do not cancel. And why don't they cancel? It is because they are acting on two different objects. Now, let us look at this one, right? Remember, this is just that small abbreviation. You don't state Newton's third law of motion like that. Now, here I have a swimmer, and the swimmer is actually swimming at the moment. Now, which one is our action force and which one is our reaction force? Now, the action force here is the swimmer's hand and the feet that are pushing the water. Remember, as he swims, he's sort of clapping the water backwards, and also the feet are pushing backwards. So the force that these muscles are applying, as well as the feet, it's a backward force. Now, if the swimmer is applying a backward force on the water, what will the water do? It will then propel, or rather it will then push the swimmer forward, and hence the swimmer is able to go forward, because if the hands and the feet are pushing backward on the water, then the water will simultaneously at the same time push the man forward. Why is that the case? Because the two forces will definitely act in opposite direction. So if the swimmer's hand and feet are pushing the man backwards, then are pushing the water backwards, then the water is going to push the man forward. And hence there we say the action force is the swimmer's hand and feet pushing the water backwards, and the reaction force is the water pushing on the swimmer's hands and feet, and that will be forward. Right, scenario here. Let us say you come and you sit on this chair. Do you agree that when you sit on this chair, you are applying a downward force on the chair? In other words, the chair is experiencing a downward force because of the person sitting. Now, what will the chair do? The chair will then exert a force on the person. And that force is definitely going to be upwards. And why is that force upwards? Because the two forces must be in opposite direction. So if the man is pushing, is exerting a downward force on the chair, then the chair will exert an upward force on the person. And those two forces will be equal in magnitude, but opposite in direction. And hence, because these two forces are also equal, we will see that the person that sits on there is not going to fall downwards. Now, what I also want you to understand is that these forces, they occur simultaneously. So it's not the action force happening, then the reaction force. The forces occur simultaneously. So when you sit, immediately as you exert the force on the window, then rather on the chair, then the chair simultaneously, meaning at the same time, it will exert a force on the person. Now, one common example is on rockets, and this they will definitely ask you in your trial examination, in your final examination, because this is a good example of explaining Newton's third law of motion, and that is in the context of technology, and hence you know, you are doing technical sciences, so we also want you to then be able to deal with these laws and applying them to real life scenarios. Now, if you look at a rocket, now when a rocket goes upwards, right, there are gases that actually come out of the rocket, right? So these red lines there, they represent, excuse me, they represent the gas that is going out of the rocket. Now, why are the gases able to go out of the rocket and actually go downwards? It is because the rocket itself is pushing the gases downwards. Now, when the rocket pushes the gas downwards and the gases actually go downwards, what happens to the rocket? The gases are then going to push the rocket upwards. The exhaust flow pushed backwards. In other words, the gases are pushed backwards. And then what will the gases do? The gases will then propel the rocket forward. In other words, there are two forces here. One force acting on the gas and one force acting on the rocket, right? By the gases, I'm talking about the flow from the exhaust. So they are acting on two different objects. One is on the gas that is coming out and one is on the rocket. So the rocket makes an action force that pushes the gases downwards, and then the reaction force is the force with which the gases push the rocket upwards. So that will be that. So this is actually the action force, and there we have the reaction force, and we can see they are equal in magnitude and definitely opposite in direction. Now, let us practice. And I want you to give me a number of action-reaction pair of forces that you see there. And I will give you a minute to just think about that. And as you think about it, I will then help you immediately afterwards. So it's 6:35. When it hits 6:37, you have thought about this, and I will be able to give you an answer. So I'm going to time you here on my stopwatch, and Your 1 minute begins now. Five seconds. And your time is up. Now, there is one one set of action-reaction pair of forces that is easier for you to see here, right? Now, some of you who are very, very inquisitive would say, Meneer, do we have an action-reaction pair of forces there between that bat as well as the ball? Now, in this particular instance, it just depends how you look at it, right? Let us just assume that there is contact at some point between these two. Now, only when there is contact between this bat and this ball will you get an action-reaction pair of forces. If there is no contact between this ball, then there is no action-reaction pair of forces. So for now, let us assume that there is contact between them. So the first, the action force will be the force of the ball on the bat, and the reaction force will be the force of the bat on the ball. So the ball exerts a force on the bat, and the bat also exerts, let's say, the force that the ball exerts on the bat is a forward force, and then it tells us that the force that the bat exerts on the ball is a backward force, right? Now, another force that exists here, this man there, is attracted towards the center of the earth due to the force of gravity. So there is the force of the earth on the man, and that force acts downwards. It is that force that we call the weight, that force that we call the force of gravity, and it goes downwards. But also, if the earth is attracting the man towards its center, downwards, then the man is also pulling the earth upwards, right? So the two forces will be equal in magnitude but opposite in direction. The other force that exists here is the force of the feet on the ground, and the feet are pushing downwards on the ground. So the ground is feeling a downward force. It's experiencing a downward force. And therefore, the ground will also exert a force on the feet, on the shoe of the man. And that force will be upwards. So I've given you three sets of action-reaction pair of forces. The first set is that between a ball and a bat. The next set is between the earth and the man. The next set is between the feet of the man as well as the ground. So those are good examples of Newton's third law of motion. Now, let us review what we basically learned for the past 4 days. So I said to you, you must be able to state Newton's first law of motion, and it states a body will remain in its state of rest or motion at constant velocity unless a non-zero net force acts on it. Just to remind you what this means, we said if the net force that is acting on an object is zero, and that object is stationary, then it will remain stationary because the net force is zero. If the object was already moving at a constant velocity, then that object will continue moving at a constant velocity. It means the net force is zero. But if a non-zero net force acts on it, meaning a net force that is greater than zero, then the object that was at rest will start to move. An object that was moving at a constant velocity will start to accelerate. It tells us. Then we moved to Newton's second law of motion. Now, Newton's second law of motion, it tells us when a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. That is the first part of the us. When there is a net force that is acting, then the object must definitely accelerate. So if there is a net force, then automatically the object will accelerate. And it will accelerate in the direction of the net force. In other words, if the net force is to the right, the object will accelerate to the right. If the net force is to the left, the object will accelerate to the left. Furthermore, it states, this acceleration is directly proportional to the net force, right? So it gives us the relationship between acceleration and net force. And that tells us if you increase the net force acting on an object, you keep the mass the same, then the acceleration is also going to increase. Now, my dear learners, you also need to be careful when you answer your questions. You increase the net force, the acceleration increases, but that relationship where we say the net force and acceleration are directly proportional, it is only true if the mass is kept constant. In other words, for that relationship there, where you say acceleration is directly proportional to the net force, it means mass must be your fixed variable, or it must be your controlled variable. They mean the same thing. And inversely proportional to the mass of the object. Now, sometimes there is a confusion. It's as if the net force is inversely proportional to the mass of the object. No, the relationship here is between acceleration and net force, and also the relationship between acceleration and mass. In other words, my dear learners, it tells me, or rather it teaches me, that acceleration is inversely proportional to the mass of the object. In other words, when the mass of the object increases, the acceleration will decrease. But that is only true if the net force is kept constant, because you cannot change the mass and the net force at the same time and then say acceleration is inversely proportional to the mass. Only the mass must be changed. The net force must be kept the same, and then you will see that increasing the mass, keeping the net force the same, will cause the acceleration to decrease. and then vice versa, decreasing the mass of the object, keeping the net force the same, keeping it constant. Let me just repeat that. Decreasing the mass of the object and keeping the net force the same, keeping it constant, will cause the acceleration to increase. So the mass decreases, the net force is kept the same, that will cause the acceleration to increase. The mass increases, the net force is kept constant, the acceleration will decrease. And that is what inverse proportionality means. Then Newton's third law of motion says when object A exerts a force on object B simultaneously exerts of equal magnitude on object A. Remember, the forces act in opposite directions, but the magnitude is the same. So, as part of our review again, my dear learners, look at this particular diagram. This is Newton's first law. Now, this kangaroo has actually jumped and it is in motion, right? Now, if this object is there, now, it will not actually remain in the air. And why will it not remain in the air? Because now there is a force of gravity that is acting on it, right? And that force of gravity, we say, it's actually the force of the earth on what? On the kangaroo. So the earth is attracting the kangaroo towards its center, and that is a downward force. Now, because of this, the kangaroo is going to go downwards. And this kangaroo, as it goes downwards, and the force of gravity is the only force that is acting on it, it means the net force here is the force of gravity, because it is the only force that is acting on the object at the time. That is obviously now if we ignore air friction, your air resistance, and so on. So the only force that is acting then when it was just in motion upwards, there is the force of gravity. So this is the net force. And because the net force is actually equal to the force of gravity, then this object will then accelerate downwards. So it cannot remain at rest, basically. It cannot remain there. It cannot remain stationary there. Why? Because now there is a non-zero net force acting on it. So it definitely has to go down. It has to start moving, because now the net force is actually a value that is greater than zero altogether. So the kangaroo there, it cannot remain at rest. Right. So that is essentially what we mean to say an object will remain at rest if the net force is zero. But if the net force is not zero, like here, then the object must definitely start to move. And even more, it must definitely start to accelerate. But the first law there is just to emphasize that it will not remain at rest because the net force is greater than zero. And that net force is due to the force of gravity. Now you look at Newton's second law of motion, right? Now, these two kangaroos, they don't have the same acceleration, right? Now, if we say, okay, the net force that both of them are applying is the same. Let's say the force on this kangaroo, the net force on this kangaroo is 20 newtons, which is the small kangaroo, it's a small mass. The net force again here, it's still 20 newtons. It means they are the muscles are giving the same net force on the object because of the force applied, right? And let us ignore frictional effects. Let's say there is no frictional force. So these two kangaroos, they are experiencing the same net force. The muscles are giving them the same net force, right? Now, because this object, rather this kangaroo, has a bigger mass and that kangaroo has a smaller mass, but the net force on them is the same, it means the acceleration of the bigger kangaroo will be smaller and the acceleration of the smaller kangaroo will be more. Why is it more? Because acceleration is inversely proportional to the mass. The bigger the mass of the object, when the net force is the same, like in this case, then the acceleration will be smaller for the bigger kangaroo and it will be larger for the smaller kangaroo. And that is if the net force is kept constant between the two. Again, you know, this kangaroo as well, it's more massive. It can actually increase its net force to be far much bigger than this one, and that can actually cause its acceleration to increase. So be aware of all of those things. Then in Newton's third law of motion, now what is happening there is we can see that our kangaroo is moving forward. Now, when it moves forward, what does the kangaroo do? It exerts a force on the ground, and that force is a backward force. Then what does the ground do? It reacts. It also pushes the kangaroo. But now, if the kangaroo is pushing the ground downwards, rather the ground backwards, then the ground will push the kangaroo forward. So the force with which the kangaroo is pushing the ground backwards with, right? The soil and everything that is on there. If it's our action force there, then our reaction force will be that force that the ground pushes the kangaroo with altogether, right? So that was actually the end of the review, as well as learning about Newton's third law and reviewing all the three laws. So just a reminder again for examination tips, I told you, you are going to get about 6 marks in multiple choice questions. You will get plus minus 26 marks in long questions. Those are your structured questions from question 2. And the total is about 32 marks out of 150. And that gives us 21% of the question paper, plus minus 21% of the question paper. And my dear learners, I'm telling you, if you go and study some more, it will definitely become a little bit easier for you. And it's really not a difficult chapter at all. And I know you will collect all the 32 marks. So lastly, we will be doing some questions again on Newton's laws, and that will be questions that encompass application of all the 3 laws. And then on Saturday, we will be concluding this topic where we will be doing a question and answer session. So with all of that, I hope that you have enjoyed the lesson, you understand all the Newton's laws of motion better, and even better for today, I hope that you you did grab this concept on Newton's third law of motion. So I want to thank you very much, and I want to say enjoy the rest of the evening. Thank you very much.